So now, as we said, we want now to determine the final state. Okay. So what we know is that H at exit is the following, and the pressure is 0.15 megapascal. Okay, so I know this property, plus that the pressure is 0.15 megapascal. So look what we will do. We will go to the tables and search for the case of P equal to 0.15. If in case H, this value, is between H saturated liquid and H saturated vapor, this means that we are in the saturated case. And in case if it is higher than Hg, which is the H for 100% vapor state, then we say that we are in the saturated, in the superheated zone. Okay. So first we need to go to our steam tables. Okay, so let us look for the saturated tables and search for the pressure entry. Here we should go to pressure entry because we don't know the temperature. So I will try to go to saturated water. Yes, pressure entry. My pressure is 150 kilopascal. So let us look here. Oh, sorry, 1 second. Okay, so this is saturated water pressure entry. I want a pressure of 150 kilopascal. So it is here. Okay, this is 150 kilopascal. Now let us make sure this table, this table is for specific volume and internal energy. So the next one will be for enthalpy. Okay, so now I will read the values of HF and HG for 150 kilopascal. So this is my line of interest here. As you can see, this is HF at 150 kilopascal. This is H at saturated liquid. This is H at saturated vapor. So the value of H here is between these two. So I can deduce that I am in the saturated state. If H was higher than 2693.54, I will be in the superheated state. Okay, so now how to find X? To find X, I say I know the value of H for my mixture. I know HF, I know HG. So I can use the formula for the quality. So here.
So doctor, just a
Yeah.
question.
Yes, sure. Tell
So
me.
if we have that H is greater than the
Yeah.
BG,
Yeah.
we
We
just
go
say that
to
X is 1.
no. Look, X is 1 means just you are in the saturated state. Whenever you are in the superheated state, you don't talk anymore about X. Okay, because you are in complete vapor. Yani we talk about X only in this phase between saturated, between 100% the point of saturated liquid and saturated vapor. After the point of saturated vapor, we don't talk about quality because X will remain 100%. Okay, we talk about superheated state in this case.
Okay.
Okay? So here, all I have to do is to replace in my equation of quality. I have H of the mixture is HF plus X times HFG, where HFG is the difference between HG minus HF. So if I replace, I have the value of H. I get HF from the table. It's 467.1. I get HFG from the table, or I can calculate it as HG minus HF. The only unknown in this equation is the quality. Then I can get the quality at exit. So I have a quality very close to 1. So I am very close from the saturated vapor state. Okay? Any question for this problem?
The question was to find the temperature at the outlet.
Yes,
no?
exactly. So we didn't finish. Yes, it's true. What you are saying is true. How you can get the temperature? Who will tell me? Going back to the figure. Look, I think they said no. They said calculate the temperature if it is superheated. Okay, but if it is not, calculate the quality. This was the question, I think. Look, determine the final temperature if the steam is superheated, but the steam is not superheated. Okay, they asked to calculate the quality if it is saturated. But if you want us to calculate the temperature, we can easily do it. You go back to the tables. The temperature will be equal to the saturated temperature. Okay, so here, what will be your saturated temperature? You can read it just close to the pressure. For this pressure, the saturated temperature is 111.37 degrees. Okay. Now, in case, let us see, let us say, in case H was higher, how can I find the temperature? Who will tell me?
If it was superheated, I get
I
the
will go to the
temperature from the
superheated
Yes,
table.
I'll go to
table.
the superheated tables. So first, I go to the superheated tables and search for pressure of 150 kilopascal. So let me check it here. Okay, this is superheated vapor water. I will search for first a pressure of 150 kilopascal. Okay, look, here for example, I don't have it. I just have, let me check, this is for H, yes. Okay, I don't have 150 kilopascal, but I have 100 and 200. So I can do interpolation in between. It's like, if you want, it's a middle pressure. I take H from 100 and H from 200 and I divide by 2. Okay. Let's say, for example, my H was equal to 3000, for example. Okay. Then if H is 3000, I will look here. I will say H 3000 is between these two here. So let's say I want 3000 in this column and I want 3000 here also, and 200 kilopascal. I want H equal to 300. If you want, how we do interpolation here? In order to do interpolation, okay, you say that for this value of H, okay, I want to find what is the corresponding saturated temperature. What is the saturated temperature at 100 kilopascal, and what is the saturated temperature at 200 kilopascal, and I can take a middle value in between. Okay, how you do interpolation? It's a linear relation. Okay, you assume linear profile. So here, for example, if you want to find what is the saturated temperature for H equal to 3000, if the pressure is 100 kilopascal, you will say that, you will write this. You say that for a temperature of 250 degrees, okay, what was H? H was 2974.33. And I know that for a temperature of 300, what is the value of H? The value of H is 3074.28. Then you say, if I want to find the value of temperature, which correspond to H equal to 3000, what is the formula I can write? Considering, if you consider a linear variation, okay, you can write that T minus 250, Okay, so you do the temperature at which you want to find H minus the first temperature over 300 minus 250 will be equal to, you will do the same thing from the other side, and you assume like a linear variation. Okay, so you have from the other side, I want to get H equal to 3000 minus, what is H for 250? The corresponding H for 250 is 2974.33 over H at 300 minus H at 250. So it is 3074.29 minus 2974.33. And in this equation, the only unknown will be the corresponding temperature at 100 kilopascal. Okay. Now, sometimes you can, if it's very close, for example, to do it in a fast way. For example, here it's nearly 2980. It's very close to. هلا هون it's nearly for 20 from 3000, and here it's nearly for 80. So you can say that it will be closer to 2974.33. But if you want to get the accurate result, you should do the linear calculation, this linear interpolation. So you do T, you get T, I will call it T1. This is the corresponding temperature for 100 kilopascal. Using the same procedure, you will calculate T2 here. And you say that to do an approximation, I will do a linear interpolation. So since 150 is just in between 100 kilopascal and 200 kilopascal, and I can say that the superheated temperature here will be also just in between. So it's T superheated will be equal to T1 plus T2 over 2. اوكي هلا هون ثاقبت 150 كمان فيها تكون 160 اذا كانت 160 ترجع بتعمل linear interpolation again. اوكي يعني هي اوقات it's a long procedure but it's يعني المethod is simple. So I do linear interpolation between values to get the values that are not present in the table. Okay.
So doctor, I use the H out in order to get the temperature?
Yes. So here H out will give you the saturated temperature, exactly, from using interpolation. Okay, but here since H out luckily was in the saturated zone, it's much easier then. Okay. Any other question on this? Okay. So now, if we go back to the problems, we are done with the first problem. Another problem. The compressor in a plant receives CO2 at 100 kilopascal, 280 Kelvin, with a low velocity. At the compressor discharge, the CO2 exits at 1100 kilopascal, 500 kelvins, with a velocity of 25 meters per second, and then flows into a constant pressure after cooling, which is a heat exchanger, where it is cooled down to 350 Kelvin. The power input to the compressor is 50 kilowatt, determines the heat transfer rate in the aftercool. Okay. So here also always the first step is to write all given. So try to do a small figure. And for example, we know that at inlet we have a condition of 100 kilopascal and a temperature of 280 Kelvin. Okay. And at the exit, we have we know at the exit of the compressor, we know also the pressure and the temperature. So P is 1100 kilopascal and the temperature is 500 Kelvin. And then we know that after this, the fluid will go in a cooler section, and it will exit at a temperature of 350 Kelvin. And I want us to find, okay, knowing that the power input to the compressor is 50 kilowatt, so we are providing to the compressor a work of 50 kilowatt. And what we want to find is what is the heat transfer rate in the after cooler. So what is Q dot of the cooler? Okay, this is the question. Okay, now first here they should add, it's missing. Okay, they should assume CO2 as ideal gas. Okay, because if they don't tell you this, you will not know if you want to use the ideal gas table or the table of CO2. Okay, here, for example, I tried to use CO2 tables. You don't have a temperature up to 500 Kelvin for this pressure. This is why here, because you cannot use the tables. Okay, it is they should tell you that we should take the ideal gas table. Okay, in general, this will be clear for you. Okay, so as you assume CO2 as ideal gas. So I will use the table we talked about together, table A.8, because it will give us properties. We just need the temperature as inlet. Okay, so we don't need to know what is the pressure, because for an ideal gas, there is a relation between pressure and temperature. So you just need one input, not both, or pressure or temperature. Okay, so, and in general, they gave us the temperature entry. So in the table, we will just go to the ideal gas table of CO2. We say that for a temperature of 280, what will be the enthalpy? We look at a temperature of 500 Kelvin, what will be the enthalpy? And then knowing H inlet, H exit, and knowing also the work in the compressor, we can get the value of what will be our unknown here. Who can tell me? In the compressor, we know nearly everything. What is missing?
The Q.
What?
Heat
No,
rate.
No, Q. Okay, Q. Look, in general, when they don't mention anything, you can consider that the compressor, if you want, is well insulated. Okay, so when they don't mention for you that we have a certain heat transfer, then you can consider that the heat transfer for a compressor is nearly zero. Okay, because in general a compressor is well insulated. So unless they provide you with heat losses, you can consider that Q is zero. What you will find is m dot, the flow rate. Okay, because if you look at the energy equation, in the energy equation, you have m dot. Okay, so here you have all properties except m dot. You have the work rate, okay, in kilowatt. So whenever I give you W in kilowatt, it is m dot times small w. So what is this unit of small w? So if you divide W dot, you can replace it by m dot times small w. M dot times small w. Small w unit will be like H, okay, because also H in this equation is multiplied by m dot. So W will be in, if H is in, so in general it's in joule per kilogram, but if you use for H kilojoule per kilogram, then W also will be in kilojoule per kilogram. Okay, so what I will do first, I will write this equation for the compressor, and I will find the value of m dot. And once I find the mass flow rate, I will use it after for the to find the heat rate in the exchanger. Okay, so here, if we apply this equation for our compressor, first, as we said, if they don't mention anything, in general, the compressor is well insulated, so no heat rate. Okay, no loss of heat. Now, I know completely properties at inlet, so I can get HI because I know the pressure and I know the temperature at inlet. Now, also in general, if they don't mention anything about velocities, you can consider that V inlet equal V outlet, so you can simplify it. And you can consider that elevation at inlet is equal to elevation at outlet, unless they specify something else. And if they give you V inlet and V outlet, then you should put it. If they give you different elevations, that you should calculate the variation. But if they don't provide any information, you just assume that they are equal. Let us check here if they gave us any information about velocity. I think, yes,
Outlet
they
velocity.
provided something. They said, yes, look, they provided something about velocity. They said that at inlet, it is entering with a low velocity. So from here, I will say that V1 is 0, is nearly 0, because they didn't specify the values. They just say that it's very low. So V1 is 0, and they gave us V2. So here, because even if we will see together that the change in velocity will not have a significant effect on the result, but since they gave us the values, so we should take them into consideration and do the calculation. So we'll take V2 equal to 25 meters per second. Okay. Now, in order to find the enthalpy, they provided me with two conditions at inlet. But as I told you, I added for you that treated as ideal gas. So I'm just interested with the temperature. So at inlet temperature is 280. I will go to the table and find what is H at inlet. And they gave us also the temperature at outlet. So I will find what is H at outlet. And then I will replace H inlet, H outlet, V inlet, V outlet in my energy equation. Okay. So first step, find H1, H2. Then I will go to my tables. And if you remember, it's not in Appendix B, it's in Appendix A, the ideal gas properties. So I'll go back to Appendix A. It's table A.8. Okay, I want A.8 for CO2. Yes, it's here. It's here nearly. No, down. Okay, that's it. So this is ideal gas properties for CO2, knowing the temperature. Okay, so the first temperature we know at inlet is 280. 280 is just here between 250 and 300. Okay, so it will be nearly 280, nearly in the middle, not exactly in the middle. So to be accurate, let us do interpolation. So to do the interpolation, all we have to do is to write this. I know that at 250, my value of H is 173.44. I know that at 300, the value of H is 214.38. So if I want to get the value of H at 280, so I should just do an interpolation. So I will write that 280. هلا when you practice كثير بتصيروا تعملوها بسرعة. 280 minus 250 30 over 300 minus 250 50 equals to, from the other side, I have the corresponding value H at 280 is unknown, so it's H minus 173, because I'm taking the value at 250. Okay, so H first minus 173.44 over now the difference between H at 300 and H at 250, so over 214.38 minus, and always at the end to verify your calculation, and the value here is close to the middle, and you should be, but it will be closer to 300 than 250. Okay, so minus 173.44, and then you can get the value of H. Okay, this is for a temperature of 280. Now at exit, the temperature is 500. So no need to interpolate because 500 is already here. So I read in the third column, it is 401.52. Okay. So from here, I know H1 and H2. Now I can replace in the energy equation. So if I go back here, also I have included the tables for you in the solution so you can understand what we used. Okay. So first, as we said, the first step is to write the energy equation for the compressor. For the compressor, I will end up with minus W equal to H2 minus H1 plus half V2 square, since no heat transfer and V1 nearly zero. So if I replace in this equation, I will get small w in kilojoule per kilogram. Okay, but I know that m dot, the mass flow rate, is the rate of work over small w. Okay, so since w dot is given, and I already now calculated why they put negative values, guys, because in general the convention we use is that work is, if work is provided to the system, we say the work is negative, while if work is produced by the system, then the work is positive. Okay, so this is here we put for W compressor minus 50 and for small w minus 203.8. So we got m dot. Okay, now once we got m dot, to find in the heat exchanger the heat rate, we will multiply m dot by small q. So the first step now, after finding m dot, is to calculate small q, then to multiply small q by m dot to get q dot in the heat exchanger. Okay, now let us go back to the given to know what are the conditions we know in the heat exchanger. So in the heat exchanger, the inlet state is state 2, which is completely defined. We already found everything at state 2. Now, at the exit of the cooler section, we know the final temperature. So as we mentioned, since we treat it as an ideal gas, we just need to know the value of temperature. So we're going back to our table. We will just read what is the corresponding value of H in this table. So for 350, I just get H from here. H is 257.9. So I will take H3 from the table, and then now I can apply the energy equation for my cooling section. Now, since it's a heat exchanger, what Q of course will not be zero. What will be zero?
The work.
The work.
Exactly, no work. No work is provided. No work is given by the heat exchanger. So now when I apply the energy equation, okay, W is, for the cooler is simplified, it's zero. So this is the general energy equation per unit, divided by m dot. So if you divide your energy equation by m dot, you get small q plus H at inlet plus half V1 square. Of course, you can add also plus GZ1, but here no change in elevation, equals to H2 plus half V2 square plus small w. Now for the cooler section, no w. And since they didn't mention anything about velocity, I will consider that velocity is not changing. So for the cooler section, my equation is simplified to Q plus H2 is equal to H3. Okay, so now going back to the application of the equation, just I want to show you how velocity is not doing any significant change. If you observe the energy equation for the compressor, look, the term half v square over 2 is 0.3. 0.3 compared to 200.5 for H2 minus H1. So this is why in general we neglect velocity variation, because it's affecting less than 0.15% your final value. Okay. So now for the cooler, okay, we will say that we will neglect velocity variation. أصلاً they didn't give us the final velocity, so we assume that we have constant velocity. And now by application Q plus H2 equal H3, we'd say that Q is H3 minus H2. We have found all values of H, so verify always your result. You should get a negative result. Why? Because it's a cooler. A cooler, when you go through the cooler, you will lose heat. Okay. Since heat is lost, then a Q should be negative, because Q, by convention, here in the energy equation, is considered positive when it's gained by the system, and considered negative when it's lost by the system. In opposition to work. Work بالعكس. If I provide work to the system, it's considered as negative. This is why when you go to the energy equation, the Q will W are on opposite sides, because we are using opposite conventions for them. Okay, so here, if you go back to the energy equation here, the general one, you have Q from the side of inlets and W from the side of outlets. Because if you provide heat, what will happen? Q is positive, increasing. So if you when you provide heat in the other side, you gain energy, so this term will increase. Okay, the whole term, I mean. So if V2 and W constant, for example, H2 will increase, because Q is positive, means it's provided to the system here. While because we use the convention for W, the opposite convention, so we take W from the other side, we put it in the side of outlet. So if I provide work, then W is negative. Okay, and this will lead to increase of H2. Okay, this is why I put W from this side. Okay, any question on this problem? Okay, now another problem. Now we will start to deal with cycles. Okay, until now we have treated each component separately, just to understand what is happening in each component. Now, in general, what is more interesting is to look at cycles. Okay, and as I told you in the beginning of the session, we have several possibilities in the cycle. We have some cycles that convert electricity to cooling or heating purposes, and others will convert heat to electricity. Now, we will start with the first type of cycles, which is the refrigeration cycle. In a refrigeration cycle, I use electricity to cool a space or to heat it, depending on the season. Okay, so this is the cycles based on any HVAC system is based on these cycles. Okay, so these cycles in general contains four main components. The first one is the compressor, and the compressor is of high importance in such plants. Okay, because it will receive the we will give electricity in order to provide work for the compressor. So the compressor will, as the name indicates, it will compress the fluid. It will increase its pressure. By increasing its pressure, you are giving it energy. This energy will be, if you want, you will see it as increase in pressure and also increase in temperature. So what you will have warm vapor entering your condenser. At the condenser level, what will happen is that your warm vapor will lose heat. So if your purpose is to heat your space during heating season, the condenser should be from the side of your internal space in order to provide heat to the internal space. Okay, then once warm vapor will go over the condenser, it will be cooled. It will transform into warm liquid. Then this warm liquid is relatively still at a relative high pressure. To decrease its pressure to be able to operate again with the cycle, I will take it through an expansion valve. In the expansion valve, the pressure will be reduced. And then after this, the cold liquid plus vapor state will enter an evaporator. At the evaporator level, here I will gain heat. Okay, so I will heat my fluid in order to, if you want, to enter again in the compressor, and to repeat the cycle. Okay, so because I need to enter my compressor in vapor state, and I am after my expansion valve, I am in a cold liquid plus vapor state. So to completely transform into vapor, I need to heat. Now, in case you want to use your cycle for cooling purposes, you will put the evaporator at the side of your internal space, because the evaporator will take heat from your environment. Okay, so this cycle can be used for cooling purposes or for heating purposes. Okay, then, and the fluid will again circulate again, so it's a closed cycle that will be repeated. Okay, now how to draw the graph for this cycle, the TS diagram. First, always in general for a compressor, okay, what is constant is the entropy. So in a compressor, entropy is constant. Okay, because I consider in general we have insulated compressors, no heat transfer. We have a, we call it isentropic adiabatic process. So in an isentropic process, S is not varying. So this is the ideal case. Okay, of course, in any real case we have losses, but with the ideal cycle we consider constant entropy. So in the compressor we will use that S1 is equal to S2 to perform our calculations. Okay, now whenever I am passing through condenser or evaporator, in condenser and evaporator I have heat exchange, I have no work. Okay, so here when I write my energy equation, W is 0. So in general for heat exchangers, W is 0. For the condenser and the evaporator, both are heat exchangers. While for the expansion valve, my expansion valve in general work at constant enthalpy. So whenever you see an expansion valve, then if you want, I will have change of phase without losing energy. Okay, so this is why I say that so here between 3 and 4,